Now in its 27th year, the school year 2024 to 2025, the Philippine Mathematical Olympiad is the oldest and most reputable nationwide mathematics competition among high school students. After its trial run in 1984, it was officially launched in 1986 and has been held annually since 2007. The country's contestants to the International Mathematical Olympiad are chosen from the top students who compete in the Philippine Mathematical Olympiad. The PMO is a project of the Mathematical Society of the Philippines and the Department of Science and Technology Science Education Institute.
Good day. Welcome to another lecture of the PMO video series. My name is Immanuel Balete, and today we will be talking about logarithms. So let's get started. We have here the usual exponential equation, and we know that when a, b, and c are integers, we can interpret this to mean that when you multiply a, b times, then you get the product c. Now, let's investigate what happens when you know 2 out of 3 of these variables. So first, if you know a and b, then it's very easy to compute c because you just, in this case, you just multiply 2 5 times. Now, what if you know b and c? So we have the equation a raised to 5 equals 32. Well, we know that you can solve this as a equals the fifth root of 32, or 32 raised to 1/5. So we can also solve the equation if we know b and c. This time, what if we only know a and c? So this time we're looking for the exponent. And this is the question that logarithms try to answer. The way the logarithm is defined is that b would be equal to logarithm of 32 base 2. So we use this notation to signify the exponent which we need, so that if you have a base of 2, you get a power of 32. Now, we can define the logarithm in a more general sense by replacing the 2 and the 32 with the general variables a and n. So logarithm of a base n is the unique real number which satisfies n raised to logarithm of a base n equals a. Or another way to think about this is if the logarithm of a base n is equal to x, this is equivalent to saying that n raised to x should be equal to a. Great. Now, here are some examples of logarithms. So the first one is from our example above. The logarithm of 32 base 2 is equal to 5 because 2 raised to 5 equals 32. Similarly, the logarithm of 25 base 5 is 2 because the exponent that you need, given a base of 5, the exponent that you need to get 25 is 2. So logarithm of 25 base 5 is 2. Now we'll look at some properties of logarithms. And these properties can be derived from the laws of exponents. So we won't prove all of them, but I'll show you how to prove the first one, and you can do something similar for the next properties. So the first property is that the sum of two logarithms with the same base can be simplified by multiplying their arguments. And it's important to note here that the bases have to be the same. You cannot use this if the bases are different. Similarly, please note that this is not the same thing as logarithm of quantity a plus b base n. So this is completely different from this, and you cannot simplify one as the other. So why does this work? This property works because if you take n raised to the left-hand side, so n raised to the left-hand side, and now using the laws of exponents, you can split this as the product of two exponents. But by the definition of the logarithm, this first one is a, and by definition of logarithm, the second one is b. So now you have n raised to the left side gives you ab. But again, by the way that logarithms are defined, in order to get a power of ab, the exponent that n would need is logarithm of AB base n. And thus you can conclude that these two exponents are equal. So that's how you'd prove this property. And the second one says that the logarithm of a raised to k base n is equal to k times log a base n. So if they have an exponent inside the argument, you can bring it out. You can bring it out and put it here. And also note that this is not the same thing as taking an exponent of the entire logarithm. So here we're only applying the exponent to the argument inside, not the entire logarithm. And last, we have the change of base property. So this is useful when you want to work in a different base. For example, let's say you have logarithm of 16 base 8. So remember, this means we're looking for the x such that 8 raised to x equals 16. Notice that 8 and 16 are both powers of 2. So you can use the change of base property to rewrite this as logarithm of 16 base 2 all over logarithm of 8 base 2. And now it's easy to simplify each of these. And indeed, you can double check that 8 raised to 4 thirds equals 2 cubed raised to 4 thirds equals 2 raised to 4 is indeed 16. So this is correct. And that's how the change of base property works. Now here are some exercises to try familiarizing yourself with the definition and the properties. I'd encourage you to pause here and try them out yourself. And now we'll give the answers. We won't explain these anymore, but the answers that you should get for these items are, you should get 0 for number 1. You should get -2 for number 2. And in number 3, they should evaluate to, if you use the properties, you should get logarithm of 2025 base 2025, which is 1. And for the fourth, if you use property 3, you should simply be able to simplify this into logarithm of 128 base 2 or 7. So these are the answers to these exercises. And now we'll look at some more challenging questions from the PMO. Here's the first from the 20th PMO. Find the sum of the solutions to the given equation, where logarithm of x is the logarithm of x to the base 10. So in the high school context, if there is no explicit base given, it is, you implicitly take this to be, usually you take it to be base 10. And as usual, please pause the video and try this out on your own first. All right. What's the hard part of this question? The hard part of this question is these complicated exponents, right? You have a logarithm in the exponent, and on the right side, to make things worse, you've got a logarithm squared in the exponent. How do we deal with this? Well, we remember that we saw earlier, if you have, using property 2, if you have an exponent in the argument of your logarithm, you can simplify it in this very neat way. So we'll use that here, and we'll take the logarithm of both sides, base 10. So clearly we want to use base 10 because that's what the question is about. Okay, and now using the property, we can simplify by taking down the exponent. So this part, this part turns into simplified here times the actual base log x equals, again, we'll take this part and bring it down here. And then multiply by the original logarithm. Log 10. There. And when you simplify this, note that this side here just turns into 1 since this is base 10. So when you simplify, you should eventually get a quadratic equation in terms of log x. And when you solve this quadratic, you should find that the logarithm of x is, the two roots of the quadratic are 1 and 2. But we are looking for we're looking for x, right? We're solving for x, not log x. So we still have to solve for x. And since we know that the base is 10, that means the values of x are 10 raised to 1 and 10 raised to 2. So together, the sum of the solutions would be 110, or letter C. Great. So that's the first item. And here's another one from the recent PMO. So we have a very interesting question here. We're given a specific logarithm, log 5 base 2, and we're asked how many positive integers k at most 100 are there, such that there are exactly 4 powers of 2 with exactly k digits. So to understand what the question is saying, it helps to list down the first few powers of 2 and then sort it by number of digits, since the question is asking about that. And you want to know, so let's list until, let's say until here. And this would be k equals 1 digits. This row is having k equals 2 digits, 3, and 4. And you want to know for which k would you be able to find exactly 4 powers of 2. So for example, this one is good and this one is good, but number 2, 2 digits and 3 digits are no good because there are only 3 powers of 2. Okay, so as usual, pause the video and try it out on your own. All right, and there are some things that you might notice when you explore this question. The first is every row always gonna have 3 or 4 numbers? Is it ever possible to find a row maybe that only has 2 values, or a row that will, maybe there's a certain number of digits where there are 5 powers of 2? Well, we can check this. Well, let's start with having 5. If you have 5 powers of 2, then this will have to be x, 2x, 4x, 8x, 16x. But note that 16x is already at least 10 times x. So from there, we already know that there's no way x and 16x would ever have the same number of digits. So it's not possible for you to have 5 powers of 2 with the same number of digits. How about if you only have, is there possible to have a row that only has 2 powers of 2? So 4x would already be on the next row. It has already an additional number of digits. Well, this would mean that 4x is bigger than, okay, k plus 1 digits would mean it's at least 10 raised to k, because 10 raised to k has k plus 1 digits. So if 4x is at least 10 raised to k, well, 2x needs to be smaller than 10 raised to k. But this first one here would imply that x is, if you divide by 4, x must be at least, okay, 100 times 10 raised to k minus 2 divided by 4, which we can simplify as 25 times 10 raised to k minus 2, or this is 2.5 times 10 raised to k minus 1. So you can imagine that x is 2, 5, and then some other digits, or at least 2, 5, and some other digits, bigger than that. However, this means that if you divide x by 2, then it must be at least one, the first 2 digits, 1, 2, and then some other digits, right? And you note that 1/2 x still has the same number of digits as x, which means that over here, 1/2 x would still have k digits. So this row wouldn't actually have only 2 powers of 2. Okay, so it's not possible for a row to have only 2 powers of 2, because you'll still be able to get divide by 2 and get another one in that row. Great. So now we've shown that every row, when you list them out, every row must definitely have either 3 or 4 powers of 2 every time. And the next question we'd like to know is, how far do we need to check? What's the last power of 2 that we need to check before we exceed 100 digits, right? So what is the p, so that this is the last power of 2 we need to check, and then after that 2 raised to p plus 1 is going to be already having 101 digits. And to answer this, all right, so we want to bound 2 raised to p to be at most 10 raised to 100, because 10 raised to 100 is the first number with 101 digits. How do we solve for p? Remember that we can apply a logarithm. So this is like solving the logarithm question, except this time it's an inequality. So if you apply logarithm base 2, because you want to extract p, so logarithm base 2, the left side just simplifies to p, while the right side simplifies to 100. Remember property 2, 100 times log 10 base 2. And now you can evaluate log 10 base 2 as log 2 base 2 plus log 5 base 2. So remember, this is, if we go back, this is property 1. You can split the logarithm based on the factors of the argument. So you have this, and then 100 times log 2 base 2 is 1. Wait, so we'll approximate, actually, because now we can use the value given to us earlier. We can now use this value over here. So log 5 base 2 is approximately 2.321. So this simplifies to approximately 332.1. So you want P to be, P should be at most 332. Because if you take 333, then it's already 101 digits. So now we know that this P should be 332. All right. So, all right, let's erase this part. So all in all, what we found is that we have to consider the powers from 2 raised to 0 until 2 raised to 332. And you know that if you put them into rows, you're going to have rows of 4 and 3. And you want to know how many rows of 4 there are. So what we can do is solve for that by using some variables. So we'll say A is the number of rows with 4 powers of 2. And B is the number of rows. Remember that every row corresponds to one value of k. And B is the number of rows with 3 powers of 2. So what are the equations we can make with A and B? Well, first we know that A plus B should be 100, right? Because you're considering a total of, you're considering a total of 100 rows from k equals 1 to k equals 100. Next, how many powers of 2 are there in all? There are 4a plus 3b powers of 2. And since you're considering from 0 to 332, there are a total of 333 powers of 2. So now solving this system of equations, you'll find that a should be equal to 33, which tells us that there are 33 values of k, such that there are exactly 4 powers of 2 with that many digits. And thus, the answer is B, 33. So that's all for this video. I hope you learned about logarithms. Thank you very much for watching.